Hello, I am Tasnim Abir, and I am going to present LiSwarm, detection and tracking of drone swarms using LiDAR. This is a collaboration work among UT Arlington, UMass Amherst, and Macquarie University. And here are my respected co-authors. They are Vu Le, Andrew Wednes Kwantama, Pranjal Sengupta, Austin Copley, Judith Joyce, Mohammad Islam, Richard Han, and VP Nguyen. So I am going to talk about drone swarm applications, challenges posed by them, and the solutions for their safe management. Drone swarms are no longer experimental. They have gone mainstream, replacing fireworks at massive public events for their eco-friendly and safe nature. For example, the use of drone light shows using drone swarms can be seen in 4th of July celebration in USA, New Year's Eve celebration in Australia, and in China, recent festivities were celebrated with a display of 14,000 drones. However, the same swarms introduce airspace complexities that are currently underexplored. Operators and administrators, they need real-time awareness of everything that is in the sky, including no-show drones or any undetected drones, and they could pose threats. Now, what might be those threats, failures, and blind spots scenarios caused by such swarms? So widespread use of drone swarms comes with some serious inevitable problems and concerns. Drones frequently create security threats at sensitive areas like airports, prisons, and military infrastructures with severe consequences. For example, Gatwick airport closure at 2018, smuggling of illegal goods under darkness in prison, and hostile drone surveillance or attacks at battlefield. Again, in civilian applications, interviews with drone show companies uncovered a critical lack of operational resilience where they need to keep track of all of their drones within the swarm. And failures are frequent there. And recovery must be done manually as the drones stop transmitting. Again, unlit drones, they also remain undetected for vision-based systems. And drones not only create blind spots to these detection tools, they are also vulnerable to attacks like spoofing and jamming, which eventually creates the same threat for security as they pose sensitive threats to sensitive infrastructures and security zones. So what are the existing solutions on drone swarm detections? What about the existing methods to detect drones and drone swarms? The first one is vision-based system. While vision-based system, they detect, these detections provide high resolution and tracking. They struggle in low visibility conditions and night time. And it is applicable only for limited number of drones with a large experimental separation between the drones. Then the acoustic-based detection system, which is robust with lighting condition, as it detects drones with unique sound signature of each drone. But it fails with ambient noise and not scalable for large drone swarms. Next comes RF-based detection systems, which is usable only for active signal emitting drones and not applicable for passive drones who hide their RF signature. And even this system can track only a few drones with even larger spacing between each drone. Again, there is a radar-based system that does robust tracking and detection for long range, but it fails to detect plastic-bodied drones, which is commonly used nowadays commercially, and also suffers from ground clutter. Then there's another modality, LiDAR. Thus far, LiDAR has been used with limited scope and used for individual drone detection mostly, and lacks scalability from swarms. And this modality is still unproven and unused for real-world drone shows and any such drone swarms as per our knowledge. So keeping all these limitations in mind, we set our research objectives that can overcome the existing limitations and respond to the existing limitations and respond to the unexplored challenges of drone swarm detection and tracking. The research objectives we listed here are to develop a low-cost LiDAR-based system, robust tracking in different lighting conditions, enabling real-time accurate detection and tracking of drone swarms, and scaling that up for thousands of drones. And this is the overview of our proposed system, LiSwarm. It's end-to-end pipeline, and it is basically comprised of 4 subsections. First comes the data acquisition subsystem. Data acquisition subsystem consists of sensor setup and data capture, which generates continuous point cloud stream, which is then fed into the next subsystem, the pre-processing, which consists of removing the clutters and isolating airborne objects. So it must remove ground, buildings, trees, or any such kind of unwanted objects, and it needs to filter out only airborne objects using z-axis threshold. And then comes the detection subsystem, which is basically divided into 2 parts. The first one is clustering subsystem, and this does the distance-aware frame concatenation to improve point density, apply spatial clustering, and also alpha shape rendering, which captures the geometry of the clusters. And in that phase, it also does the cluster characterization, which involves extraction of the centroid location and dimension of the cluster's bounding boxes. And after that, there is a drone recognition subsystem, which uses a neural network classifier. In our case, that is a modified point net with input layer fed by a 4-dimensional point cloud, and the output layer, and the output provides classes between drones and non-drones. And lastly, the subsection is tracking and trajectory reconstruction, which does the frame merging for the duration required, and then interpolation and smoothing of drone trajectories for visualizing continuous paths, even for fast-moving drones. So while designing this system, we countered obvious challenges at each step, which needed specific solutions for each of them. Firstly, for clustering, the challenge is that there will always be fewer LiDAR reflected points at large distance, excuse me, which eventually reduces the recognition accuracy in turn. And this phenomenon is shown here for 4 different distances. To handle this, we needed to use distance threshold to control the frame concatenation based on the distance to improve the point density. Point density improvement is visible here with increased frame numbers, namely 2, then 5, then 10 frames, respectively, for the same drone's point cloud. And then for the recognition, the challenge was that any cluster, recognizing the cluster, the challenge was posed by the motion blur associated within the point cloud. Due to the slow, and it is due to the slow scan rate of the LiDAR and fast-moving drones and birds. A reduction of shape-based and spatial cues due to this motion blur are shown here for a drone and a bird for a specific instance. And to mitigate this, object dimensions, centroid locations for each object cluster bounding box were considered, and the alpha shape of all those clusters were also rendered to extract more clear version of that cluster's geometry. Then comes the challenge for the classification. Here the challenge is to classify that flying object, whether it is drone or non-drone. In our case, that is bird. So we used modified point net as the neural network classifier with 4-dimensional input layer, where the spatial data is there as X, Y, Z, and the additional information is the reflectivity of the object. And then as feature extractor, we have used convolutional 1-dimensional layer. And the next challenge was posed from the tracking subsystem. And here, the tracking of the drone cluster's flight path with varied velocity created some certain discontinuities along the way while merging consecutive frames. And 2 such examples are shown as merged point clouds with 2 varying speeds and durations. And this was countered through linear interpolation to join the dots within the discontinuities, and Gaussian smoothing for any abrupt transitions due to the interpolation. And the resultant reconstructed trajectory of these 2 instances has been shown here. And the final challenge of our system was to make the end-to-end system latency to a minimum, to keep the end-to-end system latency to a minimum, and make the system scalable to increasing number of drones. To achieve real-time detection and tracking, we need to have use some innovative computer system techniques, and we make multiple directed efforts to optimize the performance of our system. Firstly, we used distance-aware clustering. And it conditions the clustering technique with a distance priority based approach, which downsamples close range data strongly and far away point cloud with weak downsampling. And to illustrate this, original point clouds and their downsampled versions for 3 distance ranges are shown here. Then we also utilized CPU-GPU load balancing. To enable faster computation, we accelerated DBSCAN clustering, which is our special clustering method using CUDA. There we parallelized the neighbor search method and distance calculations on the GPU. And there, pinned memory and asynchronous streams reduce the data transfer latency, and it enabled overlap with the computation. And the cluster characterization, which is the post-clustering task, like bounding box and centroid calculations, those were multi-threaded on the CPU and executed concurrently with GPU processing for optimum resource utilization. And to validate our system's performance in real-world swarms, we evaluate it at multiple real drone show events with the experimental setup shown here. Since all the drone light shows take place during night and in a secured area, all our LiDAR scans of drone swarms are from nighttime and from a certain distance outside that area. Here I am presenting a point cloud of the drone light show. The drone show 1 shows such a drone light show consisting of 500 drones. Drone show 2 consisting of 150 drones. And in addition to these starting layered formation of those drone shows, a specific formation of drone show 1 is also shown. And now I am going to show the results obtained from our system, both in terms of visualization and numerical metrics. Drone light shows consist of large number of drones tightly packed and typically arranged in a variety of different formations, while also transitioning conveniently from one formation to another. So LiSwarm offers the exciting possibility of being able to sense every drone, including the unlit ones, in 3D within a large drone swarm. So while the unlit drones are invisible in the RGB images at the top, those drones are clearly visible in the LiDAR point clouds at the bottom figures for the same formation with same timestamp. In fact, LiSwarm not only detects unlit drones invisible within the swarm, it also provides both location and depth information, allowing the scene to be viewed from any plane, revealing more swarm information or structures which is not fully perceived through only one viewpoint. The RGB image of this specific swarm formation at left can be viewed only from the camera viewpoint. However, the LiDAR point clouds at the right show different view planes, revealing more information about the swarm formation. So, along with sensing the drone swarms, it is possible to track the individual flight paths of the drones in 3D with LiSwarm. LiSwarm can reconstruct and visualize individual drone trajectories within the swarm based on the duration of the flight. Here, the reconstructed 3D trajectory of the selected drones within the swarm are shown for a 12-second duration. And for numerical performance metrics, we evaluated our recognition performance. To do that, we simulated a mixed swarm of drones and birds made up from real drone swarm data and bird data, point clouds. And after clustering, the inputs to the classifier was 4D, comprised of reflectivity along with the 3D spatial data. And the objective here was to classify objects as either drone or bird. So we used modified PointNet as the neural network classifier, which resulted with accuracy of 93.9% with precision, recall, and F1 score all above 90%. We also applied few conventional machine learning classifiers with customized features, and those resulted in accuracies less than 85%. Here we also used used default SLAM features for the classification to test our system with accuracies less than 59%. Upon running multiple such mixed swarm data, the neural network excelled in generalizing across diverse swarm scenarios. And after sensing and detection, we also verified the tracking performance of the system. First, we tested the spatial resolution of our system with proximity test. Among test drones, where static drones were resolved at 30 centimeter distance apart, and in-flight drones were distinguishable at less than 3 meter. So we couldn't go beyond less than 3 meter because in practice there were, these were, was triggering onboard obstacle alerts within the drone. So then we validated our trajectory's accuracy by comparing it with GPS reconstructed trajectory. And this resulted with a mean deviation of 3 meter between the LiDAR reconstructed trajectory of the test drone and the GPS trajectory. However, since GPS itself does not provide an accurate ground truth, we validated with a vision-based test where an overhead drone was used above the test drone to form a two-dimensional visual trajectory ground truth. And this showed an average deviation of 15 centimeter between the vision-based trajectory flight path and the LiDAR-based flight path. Also, but this excluded the Z-axis data. And then we tested the performance regarding end-to-end systems latency and scalability. We simulated a drone swarm comprised of 15,000 drones created from our real drone swarm data. And the system was tested without distance priority clustering and sequential processing, which is annotated by the orange bar here in the graph, with distance priority clustering and sequential processing annotated by the green bar here in the graph, and finally with distance priority clustering and parallel processing annotated by the yellow bars here. So utilizing both distance priority clustering and CPU-GPU load balancing, the time taken for detection and classification was lowest, and at a sub-second level of 400 milliseconds. Here, from these two graphs, it is from the top graph, it is shown that the majority of the processing time is taken for clustering and then for cluster characterization from the raw point cloud data. And from the bottom figure, bottom graph, it is shown that the per drone latency decreases with larger swarm size, which indicates that our system is scalable with increasing number of drones. And the parallelization is working here with larger drones. However, our system has certain limitations, such as its performance drops in rainy and foggy conditions, and our data has limited diversity in bird species and test drones data, and the drone swarm companies drones, they usually they are from same model, and we have range limitation of 220 meters due to use of vendor-specific LiDAR sensor. And to overcome these limitations, in future we are planning to accomplish these goals. The first one is including either IR or radar fusion for all weather coverage, including more UAV types and bird species to our data, and to use custom LiDAR to extend detection range. Finally, in conclusion, we present LiSwarm, first efficient LiDAR-based 3D drone swarm tracking system, an accurate, fast, low-cost, scalable detection system with sub-second processing time to monitor 3D drone swarms, which is applicable in security, entertainment, and defense. Thank you.
Okay, very interesting work, and this is Le Mi from Hong Kong PolyU. Basically, I have two questions. First, I noticed that you use like 1D CN to classify the drone, whether it is a drone or other objects.
Yeah.
So I'm curious that do you need to apply this model to every point of the detected point?
Okay, yeah, thank you for your question. So first of all, so before going into the classifier, we had the clustering phase. And using that cluster, so we were able to cluster the objects. And each cluster, they had more than 1 point. So for the worst case scenario, it had 2 points, but we didn't consider a cluster with only just 1 point. So we regarded a cluster obviously it must have 2 points. So that is worst case scenario. So most of the data, that means the clusters in our data, they comprised of more than 10 to 20 drones. And after downsampling, that was the number of points. So the classification was applied on the clusters, not a single point.
Oh, okay, so you assume that once, as long as the 1 point within one cluster is classified as a drone, so the entire cluster is a drone. drone cluster?
Sorry, can you repeat that question again?
I mean, if the classification results of the one point of the one cluster is a drone,
Yeah.
then you assume that the this cluster contains all drones.
No, no. So the shape information, that means a special clustering was used, and also the alpha shape rendering. That means since there might be some confusions when the birds and drones are flying with their wings flapping and with their propellers there might be shape confusions. So we have we have inserted alpha shape of those object point clouds as well to remove the confusions from the points. So, and basically it is not working on point by point basis, it is working on cluster by cluster basis.
Oh, okay, I see. And another question is, can we use multiple LiDAR to expand the sensing range?
That's in our future plan, because a single LiDAR, as long as the range goes, its field of view narrows down. So we are planning to expand the field of view using multiple LiDARs.
Okay.
Thank you.
Thank you.
I have time for one more question.
Hi, I was wondering if you could speak about the efficacy of the system when working with drones of varying physical size. Does that just depend on the resolution of the LiDAR sensor? Are there other limitations in the system working with micro or like nano drones? Have you thought about that?
Yeah, thank you. That's a good question. So the efficacy that we have tried to show here, so let me correct if I am answering correctly. Okay. So we have showed our efficacy result based on the drone swarm data, and the drone swarms, they are of ideal size. We did not test with any nano drones or those kind of tiny drones. So it is based from ideal size drones.
What do you mean when you say ideal size?
Ideal size means, so it is mini, that means everyday use drones. So I can name some of the names. So DJI Phantom 4. So it is, I am meaning ideal size by that.
Thank you.
Yeah.
Thank you.
Thank you.
Let's thank the speaker again. Last but not least, our next speaker